And let me check the settings. That's in okay, that's good.
Don't forget to put the date and the class that you're
yes. On top. Thank you. Okay, test speaker. All right. Got nothing. Let's check down here. Speakers are not working. That's not a problem right now because there's nobody on the Zoom in. But I wonder if this is it. Oh. Duh. Gotta turn the things on. That's good. Okay, stop test. And okay. Now let me this stuff up here. Spray. This is 17? 13. Chapter 13. EXAM7. Okay. Yeah, we're good. So let's talk gases. Did you submit your exam yet?
No, not yet.
Okay.
I'll do it today.
That's fine. All right, gases. In some respects, wait a minute, wrong chapter. And let me end up with that. Okay. We don't want to have to do that one again. Here it is. Rewind. Gases. Let's see. Come on. There we go. One of the main reasons to study gases is historical. Because when chemistry was coming out of the Dark Ages, it was transforming from alchemy to a bona fide research science. The first form of matter that was investigated with any degree of certainty in the results was gases. Gases lent themselves to study primarily because in the beginning you could investigate a gas and it didn't matter what gas it was. It would always give you the same results, whether it was air or some gas that you had collected from a chemical reaction like oxygen or later on some of the more toxic forms like chemical agents, phosgene so forth, chlorine. But they all behaved similarly. And that was good. So you didn't have to be specific about the gas you were working with. Gases play a central role, not just in keeping us alive, in the air we breathe, but gases are very often pivotal in manufacturing stuff that we use every day. Plastics, drugs, even the items that we use, like our eyeglasses, the coatings. Many of the coatings, of course, are liquids, but some of the coatings that you can place on your glasses are put there in the form of gas. They're deposited as gases. So a thorough understanding of gases is essential to understanding how the real world works and how science works. All right, so let's review. A gas is the phase of any substance which does not have its own shape, does not have its own volume. In other words, it needs a container. And any container you put a gas in, the gas will expand to fill it. It doesn't leave any voids. And of course, it acquires the shape of the container. Another characteristic of gases is when you mix two or more gases, as a matter of fact, you always get a uniform mixture, a solution. You never get a heterogeneous solution. It's always homogeneous. And the principal reason for that is there's plenty of space between gas molecules. When you put two of them together, they might not see each other for, a whole nanosecond, which is a long time for a gas. But they always form a solution. And the gas exerts a measurable pressure on its surroundings. In other words, when you confine the gas in that container, all you need is an access port and a gauge, and you can measure a pressure in it. Sometimes, depending on what you want to do with the gas, the pressure might be higher than the atmosphere around you, might be lower than the atmosphere. It could be a partial vacuum, in fact. Gases that are contained in your headlamps, the cars, are there in partial vacuum. The quartz halogen lamps are like that. I guess in a few years, I won't be able to use that analogy anymore because everything's going LED.
I hate those LED lights.
They are hard to drive against, aren't they?
Especially at night. It gives me a headache every time.
Yeah.
I'm like a deer in headlights, so even though I know I shouldn't look at them, I should look at the other side of the line.
Can't help yourself.
Yeah, I'm like, oh God, I just burned my neck now.
So, since gases exert pressure on their surroundings, and that's one of the fundamental characteristics of a gas that's confined, then we should define our terms. So a pressure is simply a force applied over a given area. And so if you have some area there and you apply a force to it, then the pressure that's applied is just that force divided by the total area. And for that reason, pressure is an intensity factor. In other words, the pressure is going to be the same everywhere on that surface. It doesn't matter if it's a bigger surface and the same pressure is applied, then that pressure will be uniform over the entire surface. But if you have a larger surface and the pressure is the same, then since the area increased, the force has to increase. Right? It's a direct, direct proportion. In other words, one increases, the other increases. Now, these are the standard units, the international units for pressure takes the form of Pascal. And that's in honor of a French polymath who must have done some work with gases or worked with pressure. But this translates into, it's a derived unit. In other words, it's derived from fundamental units. Meter is a fundamental unit of the SI system. In fact, Newton is also a derived unit. Right? So Newton represents the force, and square meters represents the area. But these are all derived units, and they're interconvertible. That's why I put this formula down here. 1 Newton, which is an N, that doesn't mean nitrogen, it means Newton in this case. 1 Newton is 1 kilogram meter per second squared. Now that's derived from actually Newton's second law of motion, which says that a force applied to a mass will produce an acceleration. So F equals ma. And if you remember that formula, you can derive these units. That's 1 Newton force, 1 mass, standard is kilogram, and acceleration is meters per second squared. So kilogram meters per second squared is equal to 1 Newton. In this class, though, we're going to be using atmospheres. It's an older unit, but it serves our purpose. And 1 atmosphere is standardized at 101,325 pascals. Right, so 1 atmosphere, to get an idea of what it is, if you at sea level, then you're probably experiencing 1 atmosphere pressure on your body. If you go below sea level, like down to Death Valley or to the Red Sea, then the pressure will be higher than 1 atmosphere. And up here, the pressure is less than 1 atmosphere because we're half a mile high. So these are interconvertible units. 1 atmosphere, or 1 ATM, is also equal to these other measurements. Right? So in order to make sense of those, we have to look at history. This Italian fellow, Evangelista Torricelli, invented a device for measuring pressure, air pressure as a matter of fact. And he took a real simple approach. Mercury was an element that was well understood, except for its toxicity. And it's a very dense liquid. So Torricelli had a bowl of mercury, and at that time, in the middle of the 17th century, craftsmen were very good at producing uniform diameter tubes. It was no problem for them. So he had one made, and he had one end of it closed off and the other end open. So he had his vat of mercury, and then he filled the tube up with mercury too, right up to the top. Then he stuck his thumb over it and submerged his hand with the tube open end down, and then took his thumb off. So this would be the tube with a closed end and open end under the surface of the mercury. And what happened? The level of the mercury dropped. Okay, so one of the consequences of doing that was this was the first vacuum. By definition, there was something there before, now there's not. That's a vacuum. But he had a reason why. Why didn't the mercury just drop all the way down? No, there must be some force applied to the surface here that is supporting that weight of mercury. Okay. He could have tried it. You can use any liquid, anything that will flow will work, but he chose mercury because it was dense. And at sea level, the distance between the surface here and there is 760 millimeters. So that's 760 millimeters of mercury is what that means for a barometer. And you could have used water, but water is less dense than mercury. So in order to get a column this high for water, you'd have to have a tube 33 feet long, minimum. Okay, that's why scuba dive. Anybody here scuba dive? Okay, that's why scuba divers say, rule of thumb, when you start at the surface of the water, you go down 33 feet. Pressure on your body increases by 1 atmosphere. You go 66 or 67 feet, average, you have 2 atmospheres. So that's useful for divers because by the time you get down to a depth where the density of water actually changes, then it's too deep for you anyway. So that 33-foot rule of thumb is valid for useful depths down to 150 or 200 feet. And some of them go to 300, but when you go that deep, you're starting to get into depths where you need something besides air to breathe. That mix in helium instead of nitrogen. Because helium won't dissolve in your tissues and nitrogen does. That's why you have to decompress when you come up too fast after being down at those depths. Your tissues are saturated with nitrogen from the air you breathe. Come up too fast, they come out of solution like that into your joints and all your tissues and in your lungs, and it just kills you. Called the bends. Okay, so Torricelli built this barometer, and then he wanted to use it, right? So he threw it in the back of his ox cart and went up the mountain. And as he went up the mountain, he noticed that the level of mercury dropped. So he says, pressure on this surface is decreasing. So air pressure as you go up decreases. And then he went from wherever he was, went down to the sea level, and it went up that time. So he said, okay. And published his work, because that's one of the essentials of modern science is once you discover something, you publish it, you make it public, so that other scientists can read your work, can benefit from your work, and take it the next step. Or they can even test your theory to see if you're all wet. Kind of like those scientists that claim to have discovered cold fusion. Remember that one? And it turns out that their science was faulty. They thought they were picking up neutrons from cold fusion in the process they were developing. As a matter of fact, they had leaks all over the place, and they were picking up neutrons from everywhere. So once that was discovered, they don't work for that university anymore. So you have to be careful. Okay, so that's what these values are for. 1 atmosphere is 760 millimeters of mercury, or 760 torr. And that's just in honor of Torricelli. Okay, so that's a better picture than the one I drew. Now, before doctors started using these automated blood pressure cuffs and the ones with gauges on them, even before they were automated, they had some with gauges so they could listen and watch the needle do like that. Before that, some offices still have these, have mercury sphygmomanometers sitting on the wall. They don't use them anymore, but they're pretty. And they have a thing of mercury in there, and you watch it. You can watch it bounce with your blood pressure. When I was younger, they still used them, so it was fun to watch that thing bounce as they were checking my blood pressure. But in order to use Torricelli's design to measure your blood pressure, all you have to do is seal this chamber. And then the only access to this surface is through an external tube that leads to a bladder in the cuff, right? And then of course you have a valve here and then a pump, right? So you pump it up. And then you watch the response here as you let the air out of the bladder, and you can measure systolic and diastolic pressure. So that's the sphygmomanometer design.
I wish they actually had one of those still, so I'm going to see it now.
Some doctors' offices still have them sitting on the wall. Yeah, and your emergency room, I think Raleigh General still has them sitting up there. Yeah. But
we just kind of use the manual one now, the cuff around the arm.
And you listen for it yourself?
Yeah, that's what we do.
Good, good. I like that. So the manometer just takes this tube and then runs it to some device where you have a trapped gas, or you may conduct a chemical reaction in there and watch the pressure as it changes. So there are many applications for Torricelli's design. They just modify them to suit your needs. And that's why the first investigations of gases were in terms of pressure and volume, because we had devices that would accurately measure the pressure, and measurement of volume had been around for decades. Okay. Oh, so there's your manometer. And you're just measuring the difference in pressure. Well, in this case, the manometer is open to the atmosphere. So when that happens, in order to know what's happening in here, you also need to know the atmospheric pressure. Right? You can see the difference in pressure from here to here, or from there to there. But to determine the absolute pressure, you need what is that value also. Okay. My father used to do this for his 8th grade earth science students. Get a paint can, put a little water in the bottom, doesn't take much, and open it up, heat it up, boil all the water, and as it expands, the steam drives out all the air, so it's just filled with steam inside. Then you cap it off and remove it from the heat and let it cool. Okay, so you've got water vapor in there, and as it cools, the water vapor condenses and produces a vacuum. So the difference in pressure from the inside and outside just crumples the can. So we can use our conversion factors. If we have 1 atmosphere equals 760 millimeters of mercury, or 760 torr, Or for that matter, we have other units of measure, right? In the imperial system, they call it 14.69 pounds per square inch, or PSI. Same thing. Is 1 atmosphere, right? So if you have these equivalences, then you can create a conversion factor. Right? It just depends on where you're starting. In this one, we're starting with 2.5 atmospheres, right? So if we take 2.5 atmospheres, we need a denominator in our conversion factor that will cancel atmospheres. 760 torr is equal to 1 atmosphere, so that cancels and gives us 1900 torr at 2.5 atmospheres, or 1.9 times 10 to the third torr. Okay? Or we could convert to pascals if we want to. I didn't put that one out here. 101.325. 1.25 pascals. P8 there. Now, do I have that in your useful information? Let's see. I was going to check myself to be sure. Conversions, 1 atmosphere. Got millibars. Yeah, there it is at the bottom. There's some others in there that I forgot about. 29.92 inches. Inches of mercury. I have to know that one because the barometer that we have in our lab over here, when CHEM100 class does their Boyles Law experiment, we have to measure the atmospheric pressure, and it reads out in inches. So I have to use a conversion factor to convert it to atmospheres. And then we measure the pressure inside our vessel with a tire gauge, so that's PSI. So we have to use this to convert it to atmospheres. Then you can add them together. Okay. So let's say the vapor pressure over a beaker of hot water is measured at 656 torr. What's this pressure in atmospheres? Right, we just have to say 656 torr. And then we need a conversion factor that will take that one and give us this one. Right? So that number should be what? Less than, greater than, or equal to 1. I'll be less than 1, right? Because they're dividing this by that. Oops. Basket. Goes the wrong button. Right, 0.863 atmospheres. My guess is that if vapor pressure over beaker, oh, it doesn't say it's boiling. Okay, so I can't make that analogy. If it were boiling, then, and it had this pressure over it, then it would probably be above sea level, considerably above sea level. Okay, now we're going to talk about gas laws. Remember the difference between a law and a theory? The law just tells you what happens. It could be in words, it says if this, then that. Or it could be in the form of a formula, mathematical expression that takes values that you can measure about your system and converts them to something else that is true for that system under those conditions. Well, that's what Robert Boyle did. In the mid-17th century, he latched on to this concept of using mercury to measure pressures of gases. So his device simply took a uniform diameter tube and had it bent into a J, like this. So this end's open, this end's closed. So when he started adding mercury to that tube, so he put mercury in here, and as he did, it formed a puddle in the bottom. He put a little bit more, and when it touched right there on the inside of that J, the gas in here was trapped, right? So he had a defined amount of gas right there. And as he added more mercury in here, he noticed that he could add more mercury over here, but the level over here did not increase at the same rate as this one did. It added more and more and more and more, and it only came up a little bit here. So he reasoned that he was getting some back pressure from the confined gas that was holding this higher than that. So once he got up to, say, I don't know, here, then you could measure how much pressure was applied to that gas inside. It's just the difference between this level here and that level. That was his J tube. And he did that for several values. Since his tubes are a uniform diameter, all he needed to know to measure the pressure was the difference in height here. And in order to know how much gas was confined in this, the volume of gas confined in here, since it's uniform diameter, remember, volume is height times area, right, for a cylinder. Remember that from geometry? The height here, area there. The area is uniform because the tube is drawn correctly. So all he needs to do is focus on height because the area never changes. So he took this height, we'll call L for length, and this height, and that's backwards. I think he said this is L and this is height. And they put him in a table and said, what's their relationship? Right? What he found was, if you measure the pressure and the volume at different positions, let's say you started off with a pressure of 1, and then you go 2 and 3 and 4 and 5. Then, and the volume started out, say, at 10. Then you notice that for twice the pressure, you get half the volume. For a third of the pressure, for 3 times the pressure, you get a third of the volume. And for 4 times the pressure, you get a quarter of the volume. And for 5 times, you get 20% of the volume. Right? So, he said, look at here. If we multiply those together, we get a constant value. See, that's just an example. I mean, that's not real data. I just made it up on the spot. But it's just to illustrate that this is true. If you multiply the pressure of a confined gas times its volume, you get a constant value. And as long as you don't change the temperature, temperature's constant, and the moles are constant. That is the amount of gas, right, and the temperature at which this is done. Keep those constant, and these two vary, and their product is equal to a constant value. So all you had to do here was just you don't have any breaks in the glass, so the mole's always the same. Right? That's easy. Temperature, you need to keep the temperature constant. So he conducted his experiments. He was wealthy enough to do this stuff without having to worry about the cost. So that means he probably lived in a nice house. In those days, nice houses were heavy masonry houses, either block or brick. And what that does is stabilizes the temperature. Kind of like going into a cave. You've been into a cave? You notice that if you go in the summer, cave feels cool. If you go in the winter, cave feels warm. It's constant all year round. So he could have conducted these experiments in a cave, for all we know. There are other ways that you can maintain the temperature. You don't have to be able to measure the temperature. You just have to know that the temperature doesn't change. One of those ways is ice bath. Ice and water together, always the same temperature, never changes. Right? So if you submerge your tube in that ice bath, it's going to hold the temperature constant. Okay. So that's in words that describes what goes on. The more detail than you probably want to know. But this came straight out of your book. It just says that if you measure the pressure here and the volume associated with it, multiply them together, then you get pretty close to a constant value. Okay, what does that graph look like? Well, if you take the pressure, of course, that's backwards. We're changing the pressure and measuring the volume. So that means this is the independent variable, this is the dependent variable. But either way, when you make those measurements, you get a curve like that. Now, in mathematical terms, geometric terms, that is a hyperbola, which means this one never touches the axis, that one never touches the axis. It gets closer and closer and closer, called an asymptotic. It gets close, but it never touches. Well, if I haven't said it once, I'll say it again. Scientists hate curves. When we can get a straight line, we're good. So, what do we do? Well, it turns out, if you look at this, in terms of what does a straight line mean, right? Y equals mx plus b is a straight line, right? There's the slope of the line. This is the y-intercept. If we just focus on this part, the slope of the line is constant. So if we say, let's see. Hold on a second. Let me focus on this one. What if we move this one over here? We can do that. Right? So P equals K divided by V. That's a valid maneuver. What if we then separate these two apart? There's your K. And this one then is 1 over V. Okay? So that's Y, that's M, and that's X. And since there's no B, it has to go through the origin. So now if we plot 1 over V against P, we get a straight line. And the slope of that line is the K. Okay? So that's what we do. We just take the inverse of the volume, plot it against pressure, get a straight line. It's easier to deal with straight lines Because if you have various values and you got your straight line drawn, you got your formula, then you can pick any other place in here where you didn't actually measure and follow that to the line and find out what 1 over V is, then take the inverse and you know what V is. Okay, now, while this is Boyle's Law, and it is true, it's not very useful. Unless you make several measurements and find out what K is. But we don't want to do that, right? Maybe we only might want to make 2 measurements, right? So if we make a measurement at this position, we find the pressure times the volume at this one equals K. Then as long as we don't change the conditions, we make another measurement. And it will give us this one. It's also equal to K. So what's that law in math? Not cumulative, distributive? I forget the name. It's like if A is equal to B and B is equal to C, then A is equal to C. That's what I'm trying to get at. So if this one's equal to that one's equal to that, then that one is equal to that one. So now you have a formula where if you take these 2 measurements and then you take one of these, then you can find the other one. Just solve for the unknown. This is what I call before and after experiment. If you know the conditions before and the conditions after, only missing one variable, you can solve for it. Later on, I'm going to show you how to solve gas equations for conditions where you're right here, you don't know what happened this side or that side, you're just right here. There's a way to do that too. But this is before and after. Boyle's Law. Okay, here's an example. Say we have a sample of helium gas and it occupies this volume at that temperature, and we don't change the temperature, and at this pressure. Then we ask, what volume will it be? Right, so we're saying this is 12.4 liters. Wait, that's 12.4 liters. And the pressure is 0.956 atmospheres. Okay. Then on the other side, what volume will it occupy at 1.2 atmospheres? There we go. So now you can solve for your V2. The trick in using these before and after equations is be sure you know what's before and what's after. These word problems, they can twist your brain around. So you got to back up and say, all right, what are the before conditions? What are the after conditions? Then you can put them in their proper places. Then it's just math. Okay, so it turns out the volume is 9.88 liters. Okay. Now, let me see, what's the point of this one? Here we're looking at volume and temperature. Okay, so we're switching. This was Boyle's Law. So we've got Boyle's Law. Okay, there we go. And that's just P times V equals a constant. Then many years later, after someone came up with a reliable temperature measurer, a thermometer, then we could start looking at the effect of temperature on gas volumes. So we've got 4 factors that define a gas: pressure, volume, temperature, and amount, moles. If you want to investigate any 2 of these, you have to hold the other 2 constant. So before we had pressure volume variables, we held temperature and moles constant. Now we're going to look at volume and temperature. That means we have to hold pressure and moles constant. So that's what Charles did. He was a Frenchman. And what he noticed was that as the temperature increased, the volume increased, as long as you kept the pressure and the moles constant. So one way to do that is have a device with uniform diameter and then a piston here. And your gas is trapped underneath the piston. And you have some force applied here, say, just put a mass up here like 1 kilogram, something like that. So that force is constant, right? And this is constant, so that means the pressure is constant. And then you've trapped the gas, so the number of moles is constant. So now we can change the temperature and watch what happens to the volume. Okay, Charles did that, and he found that as the volume increased, the temperature increased, and it was always constant. Well, this is a direct proportion. Did I say Boyles is not a direct? Boyles is an inverse proportion. As one goes up, the other goes down. This is a direct proportion, which means that when you plot the data, volume and temperature, you get a straight line. And that's what he noticed with his gases. Now, he also noticed that they didn't behave the same way with temperature. In other words, as temperature, they occupied a different volume at different temperatures, depending on which gas it was. But for the gas that was confined, the behavior was linear every time. And the slope of the line is always positive. In other words, lower left, upper right. Yeah. Okay. What he also noticed was that there was a limit, a lower limit to the temperature. In other words, if you cool the gas down below a certain temperature, it turned into a liquid. That's the end of your experiment because you don't have a gas anymore. But he also noticed that this value could not be used, could not relate one gas to the other unless you could make that temperature go through the origin. So here we have the temperature scale, which is degrees centigrade. And if we just take one gas, we could measure temperature and volume, and we could draw a straight line down to here as far as you could go. Well, Charles wasn't the only guy that was interested in temperature and gases. There was another fellow by the name of Lord Kelvin. I don't remember what his given name was, but it doesn't matter. He said, all right, let's just suppose that this gas is ideal. It stays a gas all the way down till the volume is 0. Right? Because that was one of the assumptions, that gases could be treated as if they had no particles. So he took these lines and he extended them down here like this. All right. What temperature is that right there where the volume is 0? Turns out, after many experiments, minus 273 degrees centigrade. So Kelvin said, all right, that is my new zero mark. So I've got a new scale here. It's called the Kelvin scale. That's my 0 point right there. Everything else is above 0. I have no negatives in my scale. They're all positive. So that means when you get to 0 centigrade, what's the Kelvin number? 273. And we don't say degrees Kelvin, we just say K. 273 K is 0 degrees centigrade. So that means this formula only works if you use Kelvin. And if you need to know Kelvin, you just say Kelvin equals centigrade plus 273. You don't have to use the decimals. This is going to be good enough for our work, just 273. Okay, and you can do the same thing with Charles' law that we did with Boyles' law. Before and after. That's another form of Charles' law. This is before, that's after. Just make sure that your temperature is in Kelvin. Just get in the habit. If you're going to work an experiment problem and it's got centigrade, you say, just make it Kelvin right off the bat before you do anything else. What if it's Fahrenheit, though? What do you do then? Well, you look at your useful information and you find the formula that converts Fahrenheit to centigrade. And it should be where? Where is it? There it is, upper right-hand corner. The temperature in Fahrenheit is equal to 9/5 centigrade plus 32. That's the way I memorized it. In your useful information, this is 1.8. Same thing. Now that you have that formula, if you know centigrade, you can make Fahrenheit. Or if you know Fahrenheit, you plug it in and solve for centigrade. Okay? Just learn how to use the formula. Okay, so we've got, let's see if there's any other important stuff coming out here. That's absolute zero, as a matter of fact. There we go. So let's see. Get rid of this, get rid of that. Now we have Charles' law. So that's volume divided by temperature is a constant. Move these out of the way because I need room for some more laws. Okay. 10:30. I'll be sure I can cover all our bases here. So let's. I need to move along.
I have to go to a dentist appointment. Is this all we're going to do today?
Yes. Yes, and it'll be posted by this evening.
Okay, I'll finish watching it and I'll turn that exam in for you.
Okay.
Thank you.
Okay, so for this problem, your beginning volume is 1.30 liters. Your beginning temperature is 24.7 centigrade, so you need to add 273 to that. And then the balloon you place in a flask that has liquid nitrogen at minus 195 centigrade. All right, so what's the volume now? Well, the beginning temperature is 24.7 plus 273, and the Final temperature is minus 195 plus 273. The beginning volume is 1.3, so the ending volume is your unknown. You just plug in the values, and you find that your balloon shrinks from 1.3 liters down to 0.34. All right, I've got one more. Avogadro. Okay, Avogadro came along a little later, and what he was working on was volume and moles. So he held pressure and temperature constant. Right? So Avogadro, pressure and temperature constant, and let volume and moles be his variables. And what he discovered was they were directly proportional to one another. And he said that N divided by volume is also a constant. Let's see, I better do this, because they're not the same constants. And then, of course, we can use the same relationship, same reasoning as before, to say before and after is in those terms. To solve these problems, you just have to be sure that N is in moles. Right, so there you have moles of argon gas occupying this volume. And then we wonder what volume, or V2, what will V2 be if then we only have 2.1 moles of argon. So that confined argon, you have to open the valve and let some of it out. Now, what we have here, volume on top and moles on the bottom. This relationship is just as valued if you flip it. The ratio is still the same. And we solve for the volume. Now we're going to put all these laws together into a combined gas law. And the combined gas law is going to be in before and after format. So notice that pressure times volume is a constant. But volume over temperature is also a constant. And volume over moles is a constant. So we're going to say that relationship is true. That's the combined gas law. So in this case, you can say, all right, the before pressure is this, before volume is that, before moles is that, before temperature is that, and you can change 3 of them and solve for the 4th one using this equation. Okay? Pretty simple. Combined gas law. Now that's the end of the before and after scenarios. Now we're going to look at what do you do if you don't know what happens before or after. Okay. That's where the ideal gas law comes in. The ideal gas law takes that and it fixes these values at some standard at a standard value. Okay. Pressure is 1 atmosphere. Okay. 1 atmosphere. Moles is 1 mole. Temperature is, for gases, standard temperature is 0 degrees centigrade. So this will be 273 K. And the volume of that gas under these conditions is 22.4 liters. So if you have a confined gas with these conditions, you will measure 22.4 liters. Now with those values, K becomes 0.0873, I think. To be sure. Where is it? Oh, 8206. 8206. Okay. So now we know what this constant value is with those. And since it's a constant value, it's fixed. And we can let these vary. As long as we know 3 of them, we can find the 4th one. And we give a special symbol for this one. It's called R. That's the universal gas constant. So now that we know that, we say that PV over NT equals R. And it's usually solved so that it looks like PV equals nRT. That's the common form of the universal gas equation. Now with these other laws, pressure and volume under these conditions before and after, doesn't matter what they are. You can use any values for pressure or volume. P1, V1 equals P2, V2. For this one, the only one you have to fix is the temperature. It has to be Kelvin, or absolute. For this one, just any amount that's proportional to moles and volume, any values for volume will work. But when you use this one, you have to use the units that were used to derive that R, right? So that R unit will be liter atmospheres per mole K. That tells you that your volume has to be in liters, pressure in atmospheres, moles, and temperature in K. If you honor those restrictions, then you can use this equation. All you have to do is you know 3 of these variables and you can find the 4th one. So the before and after equations, and this one I would call a state equation. In other words, we only know its present state. And that's all you need to know to use this one. Now there are other R values. And I think I might have put a few of them in here. Yeah, there's several different R values. It just depends on what equation they find in it. I mean, once the R was developed here, we found that it was useful elsewhere. So they started using R in other mathematical expressions. It just, the difference is that R will change depending on the units of measure. Okay, there's an example. You just know the current conditions and you can find out, in this tire, under those conditions, you can find out how many moles of gas are in the tire. Okay, another example. In this one, let's see, that's the combined gas law, that's ideal. I'm gonna have to erase it. there. We want to know the pressure in 304-liter tank that contains 5,670 kilograms of helium at 25 degrees. Notice that's your units. You can find out what the pressure is, but you can't use that value because that's kilograms of helium. That's mass. You need to use moles. So we just convert kilograms of helium into moles of helium and temperature into Kelvin, and we're good to go. That's a lot of atmospheres. 114 atmospheres. Whew. I wonder what PSI is for that. So 14.69 an atmosphere. 114 times 14. Whoa. 1.148. 1.148. 1.148 times 10 to the 6th PSI. Is that right? Atmosphere 14 PSI. Yep. So that would be 1.148,000 PSI. 1,000,000 pounds per square inch. I don't think that's doable. This is an exercise in intellect. It's not reality. I don't think you could build a tank that would hold that pressure, but it would have walls like 3 feet thick, made out of high tensile steel. Most tanks of gas that we used to use in the lab were maximum 3,000 PSI. You know, those tall tanks sit about this high. That's the most, we wouldn't go any higher than that. And most of them were less, like 2,000 PSI. They were still dangerous, right? We used to, a safety training, you'd see, they'd show you a film, and they'd take this big tank, set it on the ground, and they'd have this huge weight suspended over here, over the cap, over the valve. And then they'd go run behind a safety wall and pull a latch and drop the weight, and it'd hit that valve, and the pressure would come out that way, and the tank would go that way. And they'd have 2 or 3 cinder block walls over here. They'd go through all of it and keep right on going. So that was to impress on us that you want to be careful with your tanks. Okay. So in this case, moles is constant. So if moles is constant, we don't have to use the, well, let's see. We have before and after, right? There's temperature, 121 milliliters of CO2 at 27 and 105 atmospheres. Occupy a volume here at a pressure of 1.4 atmospheres. So at what temperature are we? Okay. So here we go. So this is a before and after equation. So here's the before conditions, here's the after conditions. You don't have to use the PV equals nRT for this one. Okay, another law. Just when you thought you were about to get away without. This one is Dalton's law of partial pressures. Remember John Dalton? He came up with the atomic theory. That's not all he did. He worked with gases too. What he said was that if you have a mixture of gases in a container, total pressure that you can measure on those gases is simply a summation of the individual pressures of each of the gases. Let's see, let's do this. First gas plus the pressure of the second gas plus the pressure of the third gas, and on out to however many it takes. Right? That's the partial. These are known as partial pressures. This pressure is due to one gas, this pressure is due to the second one, this one due to the third one. Just add them up and you get the total pressure. So the pressure of the gas, this actually, I'm not sure which came first, the chicken or the egg, whether he came up with the atomic theory first or he found this one first and it informed his atomic theory. But once they're both on the books, we can relate them by the pressures here are due to the number of particles, right? So if you got this gas, it's not the total number of particles, it's only the particles of that gas. So its pressure is going to be less than the total. And the same for each of the others. But when you add them all up, then these total particles gives you that pressure. So we can relate these pressures to how much of the gas is actually in there, right? What fraction of the gas is this one? And what fraction of the gas is that one? Well, it turns out that we have a fancy symbol for the fraction. It's this neat looking X. It's called the mole fraction.
When did you come up with the law of partial pressure? 1801?
Sounds right.
That's what it says on here. He's
Okay.
done the atomic theory in 1803.
Okay, so this informed his atomic theory.
I had to know. I was like,
Oh, that's fine. I learned something too. Okay, so if we know the total number of moles is 1, that's the whole, then this gas is represented by this fraction. Now let's make up a number. Say it's only 0.2. And maybe this one is the major point. It's like 0.7. Then this one would be 0.1. All those add up to 1. These are the fractions based on the moles, right? So if the total number of moles is known and each of the individual moles is known, you can calculate the mole fraction. Okay, let's see. So here's a practical application of Dalton's law of partial pressures. Say we've got some potassium chlorate in this container. It's sealed, and we're delivering the gas that's produced. In other words, when potassium chlorate decomposes, it makes oxygen. Let's see. I'm going to have to balance that, I guess. Okay, so how do I get 3 out of 2? Let's put 3 here, 2 here, and 2 here. Does that balance it? 6, 2, 2. Yeah, that balances it. So when we decompose this with heat, we make oxygen gas. And we can catch that gas here in this container full of water. So it starts out completely full of water and submerged, top down. So when the bubbles come in from this product, they bubble up here and displace the water, right? So we can measure how much of that gas is collected. The problem is, oxygen's not the only gas in that space, right? Water vapor's there too. So that means you've got oxygen here and water vapor here is equal to the total pressure. So you can measure the total pressure. If we can find out some way to figure the partial pressure of water, then we can tell how much of it is due to oxygen. Well, we do. There are charts. All you need to know is the temperature. If you know the temperature of the water, you can say, this is what the partial head pressure for water vapor is. Okay. There we go. So if we rearrange this equation, pressure of oxygen is the total minus what's the water. And all we need to know is the temperature, and we can find out the partial pressure of water vapor. So that's a practical application of partial pressure. Dalton's law of partial pressure. Let's see. How are we doing on time? Let's see. We got 30 minutes. I want to be sure I cover all topics. Okay.
Sure, I'm so sleepy.
Are you taking medicine?
No, I stayed up late last night.
Oh. Okay, all I have to do is get to kinetic molecular theory and stoichiometry after this, and we're good to go.
I'm having to dissect the pig in my lab, and it takes all week, and I stayed up last night doing that.
I see. We have to erase this one. I'll leave that one there for now.
I started getting sleepy like this. Can I stand up and just
Oh, yeah.
try to get awake?
Yeah, whatever it takes.
I got up this morning and ripped my pants. Stopping at the store. I've had a bad morning.
And let me see, did Patrick email me or text me? I don't know what happened to him. Nope.
I like this checker here.
Gases.
Yeah. When it comes to doing this stuff with math, I like math. So this should be pretty easy.
Mm-hmm. Yeah, a lot of the scientists that worked on these gas problems, in those days, I mean, they were jacks of all trades. They were pure chemists. And it helped to know your math.
Yeah.
I feel like the trade's gonna pop out on the shoe.
Oh,
On this side.
yeah. I was holding this problem because
Okay.
it needs some explanation. This is another practical application of Dalton's law of partial pressures. Say you have, wait a minute, let's go back. There we go. So you have two containers connected by a valve, and the valve's closed to begin with. And we know that this container is at a pressure of 2 atmospheres and a volume of 9 liters. And this one's at a pressure, higher pressure at 3 atmospheres, but it only has 3 liters volume. When you open that valve, they're going to mix, right? They're going to make a perfect homogeneous mixture. But their volume is going to be different. Well, the volume is going to be the same for the total, right? It'll be 9 plus 3 will be 12 liters. But the pressure is going to change. And we want to calculate what's the pressure, right? Now, intuitively, you can probably say that pressure is going to be somewhere between 2 and 3 atmospheres. But we want to know exactly what it is. So the best approach to this is treat these as separate problems, work them out separately, as if take this one and call that a vacuum, and then take this one and call that a vacuum. Then when you have the partial pressures that are due to this one in the hole and the partial pressure due to that one in the hole, you can just add them together. So that's what we're going to do, right? Right. So for the first one, pressure volume before and after is Dalton's law, Boyles Law. And we solve for the partial pressure of the 9 liter volume. It's 1.5 atmospheres. Then we do the same thing for the right-hand side, and we find out that it contributes 0.75 atmospheres. Now, according to Dalton's law of partial pressures, you just need to add the two together. And the final pressure is 2.25 atmospheres, which is what we expected, somewhere between 2 and 3. Let's see. If we start off with 27.4 liters of oxygen gas at this temperature and this atmospheres, and 8.5 liters of helium at that temperature and this many atmospheres, placed into the tank with the oxygen. Now, and the tank has 5.81 liters at that temperature. What's the partial pressure of oxygen? And then what's the total, right? So this one gives you the oxygen before and after. And this one gives you the helium before and after. And then the total pressure, just add them together. Okay. Now let's transition for a moment from laws to theories. So we need a theory that will explain these laws. Why do they behave the way they do? And the best one we've come up with so far is called the kinetic molecular theory. And with it comes, usually with a theory, comes a model. Can I explain what a model is? My best analogy is like, well, for guys, you build an airplane or build a model car or build a battleship or whatever. It's not the battleship. It's a representation of the vacuum. And once you get it built, you can make certain changes to your model and see how it affects the whole. That's what a model is. Now, in scientific models, they can be visual. They can even be three-dimensional, if that helps you understand. But they don't have to be. They can be mathematical models. So why do the things happen the way they do? Well, we need some starting points. We're going to say that gases consist of very tiny particles, atoms and molecules, but these particles are they're so small compared to the distances between them that they're virtually insignificant. The volume of the particles may be considered zero, but the particles are still there, right? Which means they have mass and they're moving. In fact, the motion we have to consider is random. The reason we have to consider their motion as random is because there are too many of them. We can't track individual particles, right? There's really, well, there are ways, but under normal conditions of 1 atmosphere pressure, there are too many particles in there to track. So we have to treat them statistically. You know, what's the average speed that they're moving? What's their average mass? And as they're moving, what do? Well, they strike each other and they strike the walls of the container. That's the kinetic part of the kinetic molecular theory. They're moving and they're striking each other. And they're striking the walls of the container, otherwise we couldn't measure pressure. Another thing that they're considered to do is that when they strike each other or they strike the walls, the collisions are elastic. What do I mean by elastic? The amount of energy that they come into the collision with is the same amount of energy they go out with. No energy is lost in the collision. It's like billiard balls banging each other. That's important. An inelastic collision would be like rolling up a ball of silly putty, drop it on the floor. What does it do? Well, not silly putty. Let's say Play-Doh is better, because silly putty will bounce. Play-Doh, you just drop it, it goes, just hits the floor, it doesn't come back. All the energy it had from here to the floor is gone. Where did it go? Well, we turned it into heat. If it were an elastic collision, we could drop it from here, it would hit the floor and come right back up to here. Now, that's theoretical. Nothing so far will do that. But there are some elastomers that will get pretty close. Those super balls, drop a super ball, and it'll go down and hit the floor. If the floor is hard, it'll hit the floor and come back up to right here.
Have you ever hit one of those against the floor as hard as you can, like throwing it and see
How high you can make it go?
I used
Oh,
to have
yeah.
some that far.
Oh, yeah.
I used to have so many of them. I don't have them.
I would do that until the thing was split.
Yeah. I was rough on stuff when I was a kid.
So those elastic collisions also assume that when the particles strike each other, they don't interact at all. They don't attract, they don't repel. They just act like billiard balls. They bounce off each other. And the kinetic energy of each of the particles, or actually the average kinetic energy of the particles in that gas, and a bar on the top means average. the average kinetic energy is proportional to the temperature. So if you increase the temperature, you are increasing the average kinetic energy of the particles in the gas. Now we can calculate individual particles' kinetic energy. All we have to know is what's the mass of the particle and how fast is it going. 1/2 mv squared will tell you how much energy is contained in that one particle moving at that given speed. That works for anything. It works for molecules. It works for bowling balls. It works for planets. So we could calculate what's the kinetic energy of the Earth. Well, the Earth is moving around the sun at a given speed. Let's say you could calculate it. I mean, it's 93 million miles from the sun on the average. So you can calculate the circumference, and how long does it take to go that circumference? Well, a year. So then you could figure out its average velocity, and then you could use that once you determine the mass. You have to look that one up. And you can find out what's the kinetic energy of the Earth. Oops. Must have accidentally punched the button again. So those are assumptions. Those are things that those are postulates, things, they're starting points for the kinetic molecular theory. So from those postulates, we're going to try to explain the gas laws. So let's say we want to explain the relationship of pressure and temperature. No one of these actually addresses that, but the combined gas law does. So the relationship of pressure and temperature is direct. As the temperature goes up, the pressure goes up. Okay, so why? Why does the pressure go up when the temperature goes up? Well, we said as the temperature goes up, the average kinetic energy of the gas goes up. It's got more energy. So when it strikes the walls of the container, it strikes them with more force, which translates into increased pressure. How about volume and temperature? Well, again, as we increase the temperature, we increase the kinetic energy, and as they strike that movable piston in our example, the piston is held down by a constant force, but the gas, as we increase its temperature, is applying more force. So the balance of the force drives the piston up and increases the volume. Let's see, I better get a move on here. Let's say we have two balloons. They have the same volume, have different gases in them. Let's see if we can complete these statements as saying it's either different or the same. So here's the first one. The pressures of the gas in the two balloons are the same or different. All conditions being equal, the volumes are the same. It doesn't matter what the gases are. The pressures will be the same. Why? Because they have the same number of particles in them. They're at equilibrium with the atmospheric pressure. How about this one? The temperatures of the gas in the two balloons are what? They also have to be the same. If the temperature changes, then we change the volume, because as we increase the temperature, the balance of forces against the atmospheric pressure on the outside is in favor of the gas confined, and it pushes and expands the balloon. But the balloons are the same volume, right? So they have to be the same temperature. number of moles of gas in the two balloons. They are also the same. In fact, that's another way of saying Avogadro's law. Avogadro said that if you have two gases confined at the same volume, at the same temperature, at the same pressure, they have to contain the same number of moles of gas. Now that work from Avogadro was taken by a young chemist named Cannizzaro. And at a meeting in Karlsruhe, Germany, at a little college there, all the best chemists in Europe came together. They were trying to solve problems that was costing industry a huge amount of money because they didn't understand the stoichiometry of their reactions. The conference itself didn't solve the problem, but this fellow, Cannizzaro, was standing at the exit, and as they were leaving the meeting, he was handing out this paper he had published. He based his work on Avogadro's principles. And they all took this paper back to their hometowns, read it, and the light bulb started going on all over Europe. They said, that solves everything. That simple relationship of pressure, volume, temperature, and moles that was proposed by Avogadro solved their problems. Okay, how about the densities of the gas in the two balloons? Do the gas laws say anything about the densities? Nope, doesn't say a thing. The only way we can tell density is, since they're the same volume, then we need to know what's their mass, right? And we know that if one of them is helium and the other one's hydrogen, the helium weighs, since hydrogen is diatomic, the helium weighs twice as much as the hydrogen. Right? So the helium density will be twice as much. They have the same number of gas particles, right? So the difference is the difference between 4 for helium and 2 for hydrogen. Okay, so there's pressure times volume. There's volume temperature for Charles' law. There's Avogadro's law, volume in moles, straight line. And I'm gonna have to skip this one. Let's skip that one. Sorry, we'll have to cover some of these topics in our reviews because we're running out of time. Okay, I already gave you the molar volume of gas. That is, if you have 1 mole of gas at standard temperature and pressure, standard temperature is 0 degrees centigrade, 273 K, pressure is 1 atmosphere, and you got 1 mole, how much volume will it occupy? Turns out it is 22.4 liters. Now, this is an important concept because every reaction that you investigate is not liquids, solids, or solutions. Some of the reactions involve gases, so it's important to know how to deal with gases in stoichiometry. So this sample of oxygen gas has a volume of that. How many grams of oxygen are present? Well, in order to find out how many grams, we can use the gas law to find out how many moles and then convert moles to grams, right? So if we have that many liters, and we know that the molar volume is 22.4 liters per mole, then we can convert that into moles and convert that into grams. We could also use the ideal gas law. Right? We can find out how many moles. All we need is conditions, 1 atmosphere, 0 degrees centigrade, 2.5 liters, and our gas constant, and we can find out how many moles, right? And then convert that to grams. So there's more than one way to solve that problem. For this reaction, we're going to take zinc metal and hydrochloric acid, and it always produces hydrogen gas. Right? So if we have 15 grams of zinc, react it with 100 milliliters of 4 molar hydrochloric acid, what's the volume of gas that will be produced? Okay, well, we've got an amount of zinc, we've got an amount of hydrochloric acid, which means limiting reactant. Probably one of them runs out first. So we have to find out what it is. All right, so there we go. So this much zinc would produce that many moles. Let's see, no, that's how many moles of zinc, excuse me. How many moles of zinc are we starting with? So how much hydrogen would be produced from that? Right? And then this is how many moles of hydrochloric acid. How much hydrogen would be produced from that? Only this much. So the hydrochloric acid is going to run out first. It produces less. So that's our limiting reactant. And we convert that many moles of hydrogen into volume using our universal gas equation, or ideal gas equation. Right? So that's how many liters of hydrogen are produced, and that answers the question. Okay, that's stoichiometry. Am I out of time already? Oh, 11:20. All right. Let's see. Oh, I thought there was more.
It's all that's in the papers that you gave us.
Okay. Okay, so next time we'll talk about, we'll review. I think. Isn't that?
Yeah, because it says the 9th, and
Today's a bonus, isn't it?
yeah, I think today's rougher. And we have a review in the test.
Okay. Did this one. Did this one today. Review on next Tuesday, and then exam on Thursday. Okay. Just on this chapter. Okay. We can stop this and let it do its conversion thing.